Okay, hello. Welcome to lecture number 13. Things are getting kind of complicated because due to an insane testing schedule, many classes are canceled and rearranged and reorganized, including, and also there have been a huge number of snow days. And so classes are a big mess, totally out of whack, different periods and different orders, etc. So I'm going to attempt to continue the video series and also get all of my classes up to date. So like I said, this is lecture number 13. I'm recording alone in a room which is weird, awkward, and sort of annoying. That means that I'll be talking to myself, I'll be asking rhetorical questions and no one will be there to answer them. I'll be going probably faster than usual when I put example problems up on the board. Please, 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 this is to my own students, pause for a second and do the problem first and then see that you got what I got, just like we would do in class. So I'm going to eliminate that thing where I wait for students to work. So please do that, otherwise you're getting nothing out of it. Watching people do math is like watching people exercise. It does not help you. Alright, that being said, to my actual students, what I'm going to do now is what I did in period 3 on Friday. So this goes out to period 8 should be the class which is watching right now. And period 8, let's see if I have this correctly, you also missed school last Thursday, and over this past weekend, over the March 1st weekend, you watched a video all about the chain rule. Alright, so let's pick it up from there. There are a bunch of homework problems on the chain rule from page 161, and I'm going to go over a selection of them now. Let's see. I will do number 13. Number 13 gives you this function, f of x equals 9 minus...
Please find the option. Can you send Lester Prosadas to sign out? Hello?
Yeah, there's no one in this room. I'm not sure where everyone is.
Okay, thank you.
Sorry. Alright, that was exciting. F of x equals 9 minus x squared to the 2/3. So let's differentiate it. Well, we have to use the chain rule. This function is something to the 2/3. So when you take the derivative of something to the 2/3, the answer is 2/3 something to the negative 1/3. Back inside for the derivative of the something, and the derivative of 9 minus x squared is negative 2x. And then we do a little pillow talk and write this out beautifully as negative 4x over 3 times the cube root of 9 minus x squared. Okay, beautiful. Hopefully that's in frame. Let's do a couple more. 17 is more or less the same thing. Let's see, 23 is a nice problem, I guess. 23 says, gives you this function, f of t equals 1 over t minus 3, and all of that is being squared. Well, I think the way to do this is to write it out in a derivative-friendly form. This is actually just t minus 3 to the negative 2. That makes it really easy to differentiate. You don't have to do the quotient rule or anything like that. This is negative 2 t minus 3 to the negative 3. Back inside for the derivative of t minus 3, which is just 1. And so the final answer is negative 2 over t minus 3 cubed. Okay, looking good. Hopefully this is helping kind of. 25, shall we, let's see, let's skip around a bit. 29, 57 through 59. Let's do 57. Yeah, 57 was the function g of x equals 3 tan 4x. Okay, let's differentiate. Well, again, the derivative of 3 times something is just 3. So what is the derivative of tan of 4x? Well, the derivative of tan of something is, we know, secant squared something. Back inside for the derivative of the something, which is 4. So final answer, 12 secant squared 4x. That's pretty easy. 58. Let's do that because it's an even. 58 gave you a function h of x, which is secant of x cubed. Okay, let's do it. Well, for this, we need to have memorized by now, or at least, hey.
Hey, how you doing?
Good.
Are you teaching somebody?
Nope.
Oh, okay.
I just grabbed this free room to do something, but I have no idea who teaches here or where anyone is or anything.
Okay.
It's an ESOL room, so if you go to the ESOL office, maybe.
What's your name again?
I mean, it's irrelevant, but my name is Will Rose.
Okay.
I just grabbed a room for no reason.
I just want that's okay.
Yeah.
Yeah, Miss Fuss, that's a teacher that's just use the room because no one's here.
Yep.
Okay, thank you.
Good. So, people think I'm crazy because I'm talking to myself alone in a room, and they are correct. Anyway, the derivative, so you need to just know what the derivative of secant is. I just know that the derivative of secant is secant tan. So you either have that memorized by now via practice, or off to the side you do a little re-derivation using the reciprocal rule or the quotient rule. But I think it's nice to just know this. And I know that the derivative of secant of something is secant something tan something back inside for the derivative of the something. And the derivative of x cubed is 3x squared. Again, these problems, once you get it, these problems are not that hard, but I don't know, they do present some confusion, especially if you're not thinking about it correctly. All right, here's a hard problem because it's like one of those triple situations. G of t is 5 cosine cubed pi t. Okay, so first of all, I would recommend rewriting this function in a way that makes the structure of it more apparent. So this is really 5 times the cosine of pi t quantity cubed. We put the little 3 there for convenience, but for seeing the structure of this, it's actually really better to write it like this. All right, and now I'm going to go to apply the chain rule. And if I'm thinking about this, I'm saying, all right, this is 5 times something cubed. Well, how do I differentiate 5 times something cubed? I know how to do that. It's 5 times the something squared. Back inside, says the chain rule for the derivative of the something. So now I have to differentiate cosine pi t. So this is a way of thinking about the chain rule recursively. That's just what the chain rule says. The derivative of 5 something cubed is, wait, I think I messed up. Derivative of 5 times something cubed is 5 times 3. One of those mistakes I warned you about. 5 times 3, bring down the 3, something squared, back inside for the derivative of the something. And what is the derivative of cosine pi t? Well, it just so happens that the derivative of cosine pi t itself requires the chain rule. So you use the chain rule when you have to, and in this case we just have to. So what is the derivative of cosine pi t? It's, well, the derivative of cosine of something is negative sine something back inside for the derivative of the something. And the derivative of pi t is just pi. So when I write this all out, I get negative 15 pi, boom, 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 times the sine of pi t times the cosine squared pi t. I think I did that right. Yep. Okay, good. More. 60, let's do 64. 64 is actually not hard, but I don't know, some people might find it difficult. This is y equals sine cube root x plus the cube root of sine x. Well, again, it's a really good idea to rewrite your function first. So this is really like the sine of x to the 1/3 plus the sine of x to the 1/3. So what is dy dx? Dy dx is going to be, well, the derivative of sine of something is cosine something back inside for the derivative of the something. And the derivative of x to the 1/3 is 1/3 x to the negative 2/3. Okay, plus I have to differentiate sine x to the 1/3. So the derivative of something to the 1/3 is 1/3 something to the negative 2/3 back inside for the derivative of the something, and the derivative of sine is cosine. Let's see if that's in frame. It is. All right, and now I just introduce a step where I just write it a little bit prettier. This is cosine cube root x over 3x to the 2/3 plus cosine x over 3, and there's really no good way to write this, so we just do it like that. Okay, beautiful. 67, kind of boring. 103, it's kind of boring. 145 is pretty interesting, but I don't feel like doing that right now. 146b, let's do 153. So 153 is determine points on the interval 0 to 2 pi at which the graph of f of x equals 2 cosine x plus sine 2x has a horizontal tangent line. All right, so where does this function have a horizontal tangent line? Well, we know that the function has a horizontal tangent line when its derivative is 0. So they're really just asking, hey man, when is the derivative 0? All right, well, I can differentiate this function. Let's do so. The derivative of 2 cosine, derivative of cosine is negative sine, so this is 2 times negative sine x. Plus, what's the derivative of sine 2x? Well, the derivative of sine of something is cosine something back inside for the derivative of the something. So I have this function, and I would like to know when this function is 0. Well, I can get rid of the 2 right away, and now I'm going to use a trick. So this is really what I have is cosine 2x minus sine x. I want to know when that's 0. Okay, this is just now completely a pre-calculus problem. Do you know how to solve this trick equation? I do, because there's an identity for cosine 2x, and in particular, the 1 minus 2 sine squared x identity is most appropriate. Because now I have something which is quadratic in sine. So if I multiply through by negative, I get 2 sine squared x plus sine x minus 1 equals 0. And hopefully that factors as 2 sine x, 1 sine x 1. I believe it does. 2 sine squared plus 2 minus 1. Let's check. So this is going to happen whenever sine x is 1/2. Boom, boom. Or whenever sine x is negative 1. And I think they asked on the interval from 0 to 2 pi. So on the interval from 0 to 2 pi, when is this true? Well, sine is 1/2 at pi over 6 and 5 pi over 6, and sine is negative 1 at 3 pi over 2. So those are my solutions. Okay, good. I now pronounce you an expert on the chain rule, kind of. Good, that didn't take too long. Pause if you need to. I'm going to erase this now. I'm going to continue with the stuff that I taught to period 3 on Friday. Cool. Good. Switch up colors. So, I will now give you a problem, and let's just, I don't know, just like see if you can do it or something. So here is a problem. Let's differentiate, sorry for a second. Yeah, let's differentiate. Let's differentiate the natural log of the square root of x squared plus 3 over x to the 5th times sine cubed x. Okay, go. differentiate that. If you're in my class, or if you're really anybody, please pause it and try for like 2 or 3 minutes to differentiate that to the best of your ability. Alright, well, it seems like this is a kind of an evil problem because it's just a gigantic, disgusting mess. Do I know how to do this? Well, assuming I know how to differentiate all of these individual functions, then the product rule, the quotient rule, the chain rule allow me to differentiate any composite combination of them. So this is not so hard, it just seems really annoying and obnoxious. What is the derivative of ln of something? Well, it's going to be 1 over the something, back inside for the derivative of the something. So now I need to differentiate this entire thing going on in here. Ugh, how do I differentiate that? Well, that's going to require a quotient rule. Inside that quotient rule is going to require a chain rule and another product rule and more quotient rules. So this is like chain rules inside product rules, inside quotient rules, inside chain rules. It is a disgusting nightmare, but there's one awesome, amazing way to do it. And that is to first simplify your function using log rules to the best of your ability. And all the important log rules are that, well, log AB is log A plus log B. Log A over B is ln A minus ln B. And the natural log of A to the B is B times ln A. Okay, this is just all like basic algebra 2, which I expect you to know. Fun exercise using the definition of natural logarithm as the inverse of e to the x. You know, prove all 3 of those using exponent rules. It's a pretty easy algebra 2 thing to do, but I'll assume that you're all experts on this. Okay, so now this becomes like a brilliant thing, right? Because this natural log can be split up. In fact, before differentiating, I can rewrite this as well. It's the natural log of root x squared plus 3 minus the ln of x to the 5th times sine cubed x by log rule 2. Okay, but I can keep going. There's no reason to stop there. This is root x squared plus 3, but this is also a log rule, right? So this is like minus, and then that's ln x to the 5th plus ln sine cubed x by log rule 1. But then log rule 3 is also relevant, right? Because this is really like ln of x squared plus 3 to the 1/2. So this is just looking so good. So this is 1/2 ln x squared plus 3 minus, bring down to 5 ln x, and then minus 3 ln sine x. Okay, this is just awesome. What I have now done is using the power of the logarithm, I have like split up this function into as many tiny little pieces as possible. And now it becomes really, really easy to differentiate. And actually, before we go any further, I mentioned this in the other class, so I should mention it to you guys too. This kind of has, there are sort of echoes here of the entire reason why logarithms were invented in the first place. It's easy to say, oh yeah, logarithms were just inverses of exponential functions, and to the extent that exponentiation is something that I want to do, then the logarithm undoes that operation, so it's a natural function to have. I totally agree. However, that was not the primary motivation or the primary use for logarithms. Some guy, okay, now I'm going to make stuff up because I haven't actually done any research yet, but this guy, I believe his first name was John Napier, which I believe is an English mathematician. He could have been French, I really don't know. Invents logarithms primarily as a calculating tool. So if you go back like 400 years, before there were any calculators, when you wanted to do things like science, especially astronomy, which is pretty much the science they had, it was very, very cumbersome to do arithmetic with very large numbers when you had to do that, when there was no calculator. So suppose I want to add 2 numbers, 51 plus 23. Okay, well that's pretty easy to do. This is just boom, 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 boom. Okay, so easy, so check. I'm happy. If you want me to add some gigantic numbers, you know, 7, 5, 2, 1, 6, 4, 8, 9, 9, 1, 7, 3 times 4, 4, 5, 5, 1, 0, 0, 8, 2, 7, 3, 1. Okay, suppose I want to add these up. Easy or hard? Answer, still pretty damn easy. Just kind of go, and you have your answer. All right, so that's great and all. Adding up numbers is fun and simple. And in fact, once you do some advanced computer science, there are ways to formally describe the addition algorithm and the rate at which the addition algorithm, or the rate at which the length of the computation grows as the inputs grow. And what you will find is that the length of the computation grows linearly with respect to the inputs. In other words, if you had to add two two-digit numbers, it takes some amount of time. But if you have to add two 20-digit numbers, those two numbers being 20 times as long, the length of the time it takes to do the computation still only increases by a factor of 10. So it's not so bad. So adding numbers is great. Multiplying numbers is harder. When you multiply numbers, you got to do this whole thing where you do a thing, and then you do another thing, and then you have to add, right? So that's still not so bad. But if I have to multiply two really, really big numbers, well, then I need to multiply the 1, and then So this is taking now like forever, right? So this is terrible. So multiplying large numbers is a really, really, really time-consuming and cumbersome process. So logarithms to the rescue. If, suppose I want to multiply A and B, what I essentially do with those two numbers is I take the log. I take the log of this product first. And if then I take the log of AB, and it doesn't matter what base log you use, natural logarithm, you could use log base 10, it doesn't matter, log base 2. Well now, this is ln A plus ln B. Well, addition is nice. It's better than multiplication. And so basically, here's what people do. If you want to multiply two numbers, what you do is you first take the logarithm of one of those numbers, and what you have is some giant massive book of which will tell you the logarithm of any number. It's a little bit more complicated than that, but these are actually not so old. People were still doing this like in the 50s, and even when I was in high school, only 20 years ago, we still read logarithms from tables. So someone produced this giant log table. Okay, that might have taken a lot of work, but once you've done it once, it's done. So you take the logarithm of a number, then you take the logarithm of the other number, so that's easily done. Let's just look up in a table. Let's just look up in a table, and now you add them. Well, adding two things is really, really easy. And adding, so when you add these two logarithms, you get the logarithm of your product. And then you basically look up this answer in an quote-unquote anti-log table. That's what they actually used to call them. And the anti-log table is just going to be the EUP table. And suddenly you get A times B. So this is how people actually did multiplication before computers. So that's kind of interesting. In addition to all the other things you learn about logarithms in pre-calculus, this is something that they don't talk about anymore because it's sort of obsolete. Yet notice how this same sort of thing is echoing over here. The principal idea of logarithms is split up products of things into sums of things, which are then easy to compute with. Here what we're doing is we're splitting up the logarithm of products and quotients into logs of sums, and now it's really easy to differentiate. So how do we differentiate this? We just kind of do it, right? This is 1/2 times the ln of x squared plus 3. Well, the derivative of ln of something is 1 over the something, back inside for the derivative of the something, minus 5 times the derivative of ln x is 1 over x, minus 3 times the derivative of ln of something is 1 over the something, back inside for the derivative of the something. And so with quite little work, I have that my answer is x over x squared plus 3 minus 5 over x minus 3 cotan x. Okay, I like to think of this as like a this is what bugs do when a fly, for example, wants to eat something. What it does is it does its digestion out externally. Instead of swallowing something and then chewing it up, it just like barfs fly acid barf all over its food, and then it sucks it up with its proboscis. That is what is going on here. When you take the natural log of some complicated thing, this logarithm is like fly vomit, which kind of just spreads everything out into just like, simple things which are then really easy to digest. All right, so that was awesome. That was awesome. There's more. What if so that was a problem. And once you're in the know, then it's clear that that's what we should do. Well, let me give you now a different problem. A different problem is this one. Okay. So now I give you a function y equals x cubed times x minus 4 squared over the 4th root of 3x squared plus 1 times, like, I don't know, tan, or 7 tan x. All right, goal, differentiate this. So I am angry at such a person who wants me to differentiate such a function because it looks terrible, and it seems like it's going to be quite difficult. Again, I have to do a giant quotient rule with product rules inside and chain rules inside of that. Man, if only there were a logarithm right here, that would be awesome, because I know that I can just decompose it. All right, so basically, if we want there to be a logarithm there, then just put it in there, just like the people did when they wanted to multiply two numbers that had nothing to do with logarithms. So now we're going to do this bold move. We're going to pre-treat this function prior to differentiating, and we're going to take the natural log of both sides. So what is this? This is ln y times the ln of this giant mess. Well, when I take the ln of this giant mess, I can now proceed as before, simplifying this. So I hate to keep repeating myself, but please be following along, like with a notebook, taking notes as you normally would. And do this problem. Pause the video for a second, do the problem, unpause it, because I'm going to just go really fast. So this is being fancy and showing off because I'm experienced. Now that I said that, I'll probably mess up. But you know what? I think that's right. So boom, 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 boom. Yeah. Everything breaks up really, really nicely. Hopefully you got the same thing. Okay. Now that everything is really simple and easy to differentiate, I'm going to differentiate both sides. But we have to be a little bit careful now. So what I'm going to do, like I just said, what I'm going to do now is I'm going to differentiate both sides with respect to x. Alright, and we did this one other time in this class, and it's a little bit subtle, so let's talk about it. Oh, sorry, differentiate both sides with respect to x. So I'm going to take the derivative with respect to x. Okay, well, so let's go over here to the left. What is the derivative with respect to x of ln y? It's tricky and complicated until you get used to it. So the derivative with respect to x of ln y, well, so fact. Here's a fact. The fact is that the derivative with respect to x of ln x is just 1 over x. So that's the rule for the derivative of the natural log, which we proved. But what is does it matter that this is a y? Well, it does matter because we're differentiating with respect to x, not with respect to y. So you need to be sophisticated enough to understand that this is a y. This y is itself a function of x. And so when I take the derivative with respect to x of ln y, well, you have to say, okay, what is the derivative of ln of something? The derivative of ln of something is 1 over the something back inside for the derivative of the something. And the derivative of y is dy dx. And by the way, dy dx is the thing that I wanted, right? The whole goal of this problem was to differentiate. So that's what I want. What I want is dy dx. Right, my experience is that people find this kind of weird. So what you just need to do is just kind of keep in mind, suppose someone just asked me to differentiate like the ln of, I don't know, sine of x, for example. Well, what is the derivative of ln of sine of x? Well, now I'm sort of aware that the chain rule tells me that this is going to be that the derivative of ln of something is 1 over something back inside for the derivative of the something. That is exactly what's going on here. The derivative of ln of something is 1 over the something back inside for the derivative of the something. And the derivative of y with respect to x is dy dx. So if you're comfortable with this, and hopefully you are, if you understand the chain rule, then you should be comfortable with this too, because it's really just the same thing. I'm just leaving y general. Okay, this is called, this has a name. This is called implicit differentiation. And we're going to talk more about this differentiation. We're going to talk more about this later. Or we're going to see how other things that this can do. Okay, so now differentiating the right-hand side is just a problem which we can do. This is just 3 over x plus 2 times the derivative of ln of something is 1 over the something back inside for the derivative of the something, which is 1. Minus 1/4 derivative of ln of something is 1 over the something back inside for the derivative of the something, which is just 6x. Derivative of that is 0 minus the derivative of ln of something is 1 over something back inside for the derivative of the something, which is secant squared x. So now I get this gigantic thing. Let's see. And now what I want is dy dx. Well, what is dy dx? It's going to be, I have to multiply through by y, and the y is just this original thing. And so my overall answer, x cubed, x minus 4 squared, over 4th root 3x squared plus 1 times 7 tan x times all this stuff. So 3 over x plus 2 over x minus 4. I never said it was going to be pretty. Minus 3 over 2, 3x squared plus 1, minus whatever secant squared over tan is. Let's see. Cosine goes up. Oh man, it's too hard. Sine over cosine cubed. So what is that? Tan. Wait, no, it's